Alrighty, so we're going to do a bit of a technical deep dive into the rotor encoder steering wheel controller. Now, I've designed this whole thing with KiCad, and I'd highly recommend KiCad. It's such a powerful tool, and it's really cool that it's open source and you can contribute to it. So I'd highly recommend looking into it, and if you can and are able to, help with some contributions, even to some extensions. So I designed this whole schematic just on the one page. I think it's simple enough that we can get every bit of detail across without having to do a hierarchical design. And so what you can see is that I've gone for a very standard flow pattern as well. So we've got all our inputs on the left and all our outputs on the right, and in between is all the processing. So we'll start with probably the most complex. I mean, it's not even that complex, but we'll start with the USB connector. So we've gone for a USB-C connector, and this handles both data and power. So most importantly, with USB-C specifications now, you need to have the CC lines pulled down if you ever want to pull any power on the lines, and each line needs its own resistor, 5.1K. You must do this so that you can pull power. In a proper design, you'd also swap these out for an actual communication chip to negotiate what your power requirements are. But this is a bit of a hack. And you have to do this if you want to draw power, and it sucks to see some companies haven't done this and they've cheaped out on this, but you must do it. Since we're dealing with a connector and inherently humans are notorious for building up static charge and dissipating it through electronic components. So on the data lines, we've also got this TVS diode array, transient voltage suppressing diode array. And what this achieves is it clamps the voltage to a reasonable level if we do see spikes from events such as ESD events. The chip I've used, it's pretty jelly bean style. This is a very common chip that quite a few people use. And if you click on it, you can find its part number, manufacturer part number, and the LCSC part number as well. So I order all the components from LCSC, and we include all this information in here and the data sheet as well. So on this power line, we've also got a reverse polarity protection diode and a fuse, and USB-C specs are that you can only have 10 microfarads on the V-bus line. And I've kind of skewed away from that a little bit here. I chucked this 100 nano cap as well, just to stabilize this USB power rail. Should it cause issues? Probably not. But yeah, I guess we'll see. Decided to go for a linear regulator for this design. We've got hardly any power draw, which results in not too much power being dissipated either, so the heat management is perfectly fine. And you'll find in my designs that I put some notes in detailing part selection and why we've chosen the part and any key parameters to calculate. So we can see here that because of the ultra low current we're drawing from it, we're well within the thermal spec of this chip. I've gone with the Texas Instruments chip. TI have just got a very good reputation, and so for a product like this, I want to go with a well-known brand that produce reliable and high-quality products. So again, you can see all the information here, part numbers, LCSC part numbers, and data sheets as well. But one of the gotchas with this regulator, and quite a few linear regulators, is that there's a minimum current draw for the output voltage load regulation to be within spec. What does this mean? Well, if you don't have a load across the output, or if your load's too low, the output voltage and the regulation of this output voltage, should I say, it's not good. It's not good, and I found this out by not having a minimum load across this. And what you see is that the output voltage will just rise or fall and not be within spec. So how can we load the system up all the time? Well, we could chuck in this cheeky LED and resistor, and this will produce a constant current load on our output and put us within the spec for minimum regulation. This means that the output from this chip will actually be 3.3 volts plus or minus whatever they say based on their 1 milliamp regulation load. Our USB data lines enter this transceiver chip, and this converts our USB differential pair signaling into a stock standard UART signal. But the chip we're using is an ATtiny 414, and to program it we need a UPDI signal. Now the UPDI protocol is strangely similar to just a regular UART signal. It's practically a single wire serial communication line. And I've popped in this link here which goes into more depth on how this whole system works, and I'd highly recommend looking at this, but these guys have done a lot of the groundwork and research into how to create these circuits, and this lets us just directly program this ATtiny just with USB, and life is made so much easier. You'll also notice throughout the schematic I've got all these test points. This just lets me probe these signals really easy with an oscilloscope rather than fiddling around with the actual pins on the chip. There's somewhere nice and exposed on the board for me to test. The encoder connects here with this JST header, and once again, because it's a human facing port, we protect it with some TVS diodes. We also do some hardware RC filtering of these lines. I like this because we can actually filter out any noise spikes from this encoder and reliably trigger interrupts. So we can run this whole system asynchronously without needing to do any polling. If you want some more explanations on this, I'm more than happy to do even more of a deep dive, but rest assured this makes your life easier when designing software. Though if you remove this to change the software, it's not too hard. You just need to understand what you're doing. And there's plenty of examples online and lots of forums and lots of instructions on how to do something like that. The 414 from the ATtiny 414, it's a really easy microcontroller to use. And as you can see, we've just got the VCC line, so 3.3 volts, decoupled with this 100 nanofarad capacitor, and then a programming line, and that's quite literally all you need to get this running. But we've popped in some extras, so we've got some status lights as well, just so we know what state we're in, and it's good for some visual feedback. The last thing really in the schematic is the steering wheel control outputs, and so this device works with head units that support resistive steering wheel control learning. So you can see we've got 3 output resistors here with different resistance ratings, and here we've got 3 MOSFETs, so N-channel MOSFETs. These act as digital switches to ground, and it's important to know it's to ground. So we use these switches to change the resistance on our steering wheel control output line, and head units also have a pull-up resistor, and so by doing this we change the voltage that appears on this line. If you want to find out more, Google voltage dividers and you will be able to work out how this actually works. And so because we've got these 3 different values, we can create 3 different voltages on this line. So let's dive into the board and the layout. So with the board, I've tried to keep it as simple as possible. We've done every single bit of routing all on the top layer. And we've kept the bottom layer as a solid ground full. Now, this is really important when it comes to circuit design because you have to think of circuits as signaling using potential energy. I think it's important to think, you can't really just think of signals as signals going here. The signal actually occurs in 3 dimensions, and it's the differential energy between these points. So if we have a cut in this ground layer right here under this data negative line, the potential energy between these signals has to travel all the way around this cut. And this extra travel is what really causes noise in our systems. I'd highly recommend looking up Rick Hartley on YouTube. He does some brilliant seminars on what causes noise in systems and how to properly ground a system. But the best rule of thumb I find is keep an uninterrupted ground plane under every signal layer. And so that's what I've done here. So we've got a completely filled ground layer underneath our signal layer. And I'm not really going to go too much into how this is designed, but you can see in the 3D view as well, we've got mainly our inputs and our outputs, and then a microcontroller sitting middle. There's not really much to it, unfortunately. This is something, if you want more information on, I'm more than happy to either run up a new video or answer in the comments. Only things to really note are the USB differential pairs. We're operating at USB 2 speeds at a maximum, and so given how short these data lines are, it doesn't really matter too much that we aren't following a fully differential pair routing. We just keep these lines nice and short, keep our stubs as small as possible, and because we are not dropping down to the bottom layer with a via, I think this is perfectly fine. If I'm wrong, feel free to tell me in the comments, but that's probably the fastest signal we have on this board, to be honest, and the only one of importance. So that's pretty much everything covered. Again, if you have any questions or any suggestions, or if you want me to cover any more topics, just let me know in the comments and I'll be more than happy to spin something up for you.